Awesome. So we're the Autonomous Delivery Robot team. I'm Ryan Schuler, and I'll be talking about the background of the project as well as some of the design. But before I begin, we wanted to give a special thanks to Bob Terhune and Jimmy Gill from Uber's Advanced Technologies Group, Mr. Scott Gillette, who runs the Electrical Engineering Senior Design Lab, and Dr. Timothy Moore for assisting with the project, and of course to our advisor, Dr. James Brooks. You've been a great help through this whole endeavor. So moving on to the background of the project. Lots of packages are delivered to campus daily for students and faculty in Hoyt Hall to use in projects and research. Mr. Jim Peich, the machine shop technician, spends about an hour each day handling these packages between fetching them from the student union and distributing them to students and professors in Hoyt Hall. So the idea for this project arose from this issue as well as the donation of two Velodyne VLP-16 LiDAR sensors to the engineering department from Uber. So although they're best known for the taxiing business, Uber also does a lot of work in robotics and commonly uses LiDAR sensors to serve as the eyes of a robot. If you're unfamiliar with LiDAR, it stands for light detection and ranging, and is just a method of using lasers to measure distances from a sensor. So overall, the general idea of our project is to create a robot which can deliver packages from the Breen Student Union to Hoyt Hall, saving a significant amount of time for Mr. Peich. So moving to the requirements and specifications. In any large project like this, defining good specifications at the start is very important, and our specifications define the end goal for the delivery robot project. We feel that the four basic statements on this slide summarize those specifications well. We need the robot to be remotely controllable from a simple user interface system for convenience. For the robot to be beneficial for Mr. Peich, it must be pretty easy to start and stop from a distance. Once the instruction has been given to navigate to one building to the other, the robot should be able to get itself there using some navigation method. Thomas will discuss the navigation system we use in greater depth later. From speaking with Mr. Peich, we learned that the packages he receives are as large as 2 feet by 2 feet by 2 feet and up to 40 pounds in weight. He also sometimes receives tube-shaped packages which are 6 feet long and 4 inches in diameter. The final robot must be able to accommodate both of these types of packages. And finally, as you may know, the weather in Grove City, Pennsylvania varies quite a lot, and we felt it necessary to require that the robot can handle rain, snow, and cold or hot temperatures without degrading. Moving on to major subcomponents next. So this diagram you see on your screen is a physical representation of the robot. All of the blue blocks are implemented in the current prototype, and yellow blocks will be implemented in the future. The arrows simply represent communication or connection between the two systems. The blue blocks will all be discussed in greater detail later in this presentation, but to briefly touch on some of them, the Jetson Nano, that big square you see in the middle there, is the main computer in the robot. It runs our software and communicates with the GPS RTK system, the user interface, and the Arduino. The GPS RTK receiver is a small system that works with a base station on campus to track the robot far more accurately than traditional GPS would allow. This is necessary for the navigation system to do its job. The Arduino Uno is a small microcontroller that we use to control the motor controllers at a low level through PWM signals. And the user interface is hosted on a web server from the Jetson Nano and is how users will start or end navigation functions on the robot. Due to time and budget constraints, the components in the yellow blocks were not able to be implemented this year, but should be very manageable for the next delivery robot team to add. These components would allow the robot to communicate better with pedestrians, as well as safely transport packages. And now I'm going to hand this off to Devin to talk about some of the subsystems in depth.
Thank you, Ryan. As Ryan mentioned, Uber was able to provide us with a Velodyne VLP-16, which is a LiDAR capable of seeing up to 100 meters away. This was tested and verified by Thomas and Ryan together, and it is in fact able to see objects up to 100 meters away. It outputs data at roughly exactly 300,000 data points per second, with each data point consisting of X, Y, and Z polar coordinate data. Cartesian coordinate data. This type of information allows us to map out our surroundings using the LiDAR's feedback and see where exactly objects are with respect to the LiDAR itself. Because the LiDAR is mounted on our robot, it allows us to compare objects with where a robot is so that we can avoid any potential collisions. For our purposes, we chose to use this LiDAR primarily for collision avoidance purposes instead of primary navigation purposes. For outdoor navigation, as Thomas will talk on later, we used the GPS RTK system, but in the future, it could be possible to use this LiDAR data for indoor navigation, possibly with computer vision or some comparable algorithm. To process this much information, we needed a computing platform capable of processing these 300,000 data points per second. To meet this need, we set out to find a computing platform capable of processing this information accurately and in a frame rate at a rate quickly enough for our robot to respond to. So one of the platforms that quickly jumped out to us was the NVIDIA Jetson Nano. And to test it, we actually had one on hand provided by Dr. Rumbaugh, and we used it to compare against a Raspberry Pi 4, which is a computer of similar cost and specifications. To test these computing platforms, we ran the same software on both sides, including some proximity checking from the LiDAR data, as well as visualizing the data through a program called RViz, which allows us to map out the data. And we performed, we downloaded an open source, off-the-shelf object detection algorithm. While our final implementation does not use this object detection algorithm, we wanted to leave the door open in case we decided to turn in that direction or in case a future design team would decide to go on that route. And we wanted to leave that door open and make sure that the computing platform that we chose now would be able to process that in the future at a high enough frame rate. In almost every metric that we compared the Raspberry Pi 4 and the Jetson Nano, primarily consisting of the percentage of resources used for this computation, the Jetson Nano outperformed the Raspberry Pi. This led to us choosing the Jetson Nano as both being capable of processing our data and being within a reasonable cost. Due to the cost of the chassis, we had to pick a computing platform that didn't eat away at the budget, and so this proved to meet that specification nicely. On the Jetson Nano, we are running a form of Linux, Ubuntu 18.04, and we ran the desktop environment that is provided by NVIDIA for the Jetson Nano on this operating system. And on these operating systems, we downloaded ROS and set up a ROS node network, which is our operating system. So Robot Operating System, or ROS, is an operating system that aims to make programming robots specifically more straightforward. From a practical standpoint, one of the largest benefits of using Robot Operating System is its function of being able to pull this large-scale idea of wanting to move this robot from one building to another it allows us to break that end goal into much smaller, more manageable subcomponents. On this diagram on the left, you can see the blue nodes, the blue figures rather, that those represent our ROS node, and the green squares, rectangles, represent what are called ROS topics. The way ROS functions is you set up each ROS node to represent a physical component and or a specific function of the robot, such as the motor controllers, the navigation software, the intake from the LiDAR sensor, as well as the proximity checking, and things like that. The way these nodes communicate with each other is through what are called ROS topics, which are simply pieces of information, such as a sentence, a string, a Boolean true or false value, or a number, such as an integer. An example of this is our proximity checking node, which subscribes to the ROS topic Velodyne points, which is the LiDAR data outputted by an existing ROS library that interpreted the data from the LiDAR. So the proximity checking node subscribes to that data. It interprets it. It gets the X, Y, and Z coordinate values and compares them with the LiDAR to make sure they are not too close. For our testing purposes, we used about 1.5 meters as our barrier, if you will. And the proximity checking node publishes to the topic proximity. Excuse me. It publishes in the form of a string Boolean and lets the motor control node know if there's anything that is too close to the robot that could be dangerous. And so that way, since the motor control node subscribes to this topic, it can know immediately that something's too close and we need to stop the motors now. The master node coordinates all of the subnodes by assigning them each a specific name and also keeping track of each of their ROS topics. So it keeps a list of which nodes are publishing which topics, but more importantly, it keeps a list of which nodes are subscribing to each ROS topic. And that way it can notify these nodes as soon as any new information is published. I'm now going to pass it off to JD to talk about the chassis and the power system.
Thank you, Devin. So for the chassis, we had a few requirements, and that the first being that it had to be able to traverse the path between the buildings. And the second was that it had to be large enough to put a carriage on to hold those 2x2x2 packages. So we chose a Raptor track drive unit. You can see this unit in the photo on the bottom left. On this, we utilized 4 2.5-inch SIM motors and two 12.75:1 ratio gearboxes. With this configuration, the chassis can reach roughly 4 miles an hour, so fast walking pace. Each motor has its own Spark electronic speed controller, and this just takes power from the batteries and passes it, and based on a PWM input, can set the speed of the motors. So we powered this whole system from two 12-volt, 18-amp batteries. We used 2 instead of 1 because the smaller batteries allowed us to sort of fit them off into kind of crevices in the package so we could fit it around the packages, or in the carriage so we could fit around the packages. So as you can see in that photo, there was no provisions for mounting any electronics to. So thanks to Mr. Gillette, we were able to get sheet metal made in between the two cross members to mount all of our electronics to, and then also to protect them for our weather resistant requirement, we have a skid plate that goes below that plate, and then another box that can actually slide over the top and get screwed down. You can see this box in the photo on the right. So now on to the power system in more detail. Our power system consists of 2 main subsystems. The first of which is the motor system, which has those electronic speed controllers, a fuse block, and a bunch of relays. So power is brought in through the fuse block. This limits us to 120 amps in total, 30 amps a motor, which is just under what we should see under really, really heavy load, or just over rather. Now, each of these speed controllers, in between the fuse block and the speed controllers, we have a relay. All of these relays are hooked up to a kill switch. So you can hit the kill switch and shut off the speed controllers to get disconnected from the batteries. Now, the other side of our power system consists of a board that is set up with a 5-volt regulator. So this drops from the 12-volt of the battery to 5-volt to power the Nano. The Jetson Nano then has another wire running to a relay, which then controls the power system for the LiDAR. So this means that we can programmatically turn it off. So say we get to our destination and we're going to sit there for a while waiting for someone to show up. We don't want to be burning power or just spinning the LiDAR when there's no use for it. So we can actually shut that off and save a little bit of power. This also gives us this total system also gives us the ability to shut off individual things separately. So say you hit the kill switch, then we don't shut off the nano. The nano can actually be gracefully shut off, and that won't cause any sort of software issues. So next we will go on to the motor control. So motor control happens across sort of three systems in parts. So the first would be the actual physical chassis. Again, we have the spark speed controllers. So these take in a PWM input from what I'm going to call the second system. And the second system is a Arduino and a Bluetooth chip. So the Arduino has a script on it, which creates these PWM signals. So PWM is pulse width modulation. And these signals run at a frequency between 100 hertz and 200 hertz. And they have a pulse width between 1 millisecond and 2 milliseconds. So 2 milliseconds has the speed controllers telling the motors to run at full speed forward, and 1 millisecond is full speed backward. In between is sort of a linear range for that. So 1.5 is neutral, and 1.75 would be half speed forward. So the Bluetooth chip I had mentioned works with the Arduino to actually be able to override our automated control. So say it gets stuck, you can take, I have it paired personally to my phone. So I can take out my phone and use a serial communication app to actually manually reverse it out of where it's at, drive it where we need it to, and then assess the situation from there. So then that last piece I had just mentioned is the nano control. So this is a motor control ROS node that takes input data from the navigation and the LiDAR and actually decides on how we want the system to move, because that Arduino is simply functional in that it only has functions that say go forward, go reverse, stop, turn left, turn right. And so this the nano node actually makes these decisions on how to progress. So now we will go on to Thomas to talk on navigation.
Thanks, JD. So the navigation is implemented using GPS RTK. The RTK stands for real-time kinematic. So that's just a fancy name for differential GPS. The reason we are using this is because GPS typically is not especially accurate. It's usually accurate within a few meters. And so what we are doing is we have a base station with a fixed location, so it knows where it is, and then it's able to take the information from the GPS satellites and then find the difference between where it thinks it is and where it knows it is. And then it's able to send that information over low frequency radio to a rover unit, which is mounted on our robot. This rover unit is then able to use this information from the base station to correct its own data that it's getting from the GPS satellites. So it's all well and good that we have highly precise positional data coming into the robot, but then we need to figure out the problem of how do we get to our destination. And the way we're doing this is we have a set of discrete points, which we have already mapped out between Hoyt Hall of Engineering and the student union. And so what happens is we have a file with all of these points, and the first one is loaded from the file, and then the robot, that's going to be point N right here, and then the robot knows where it is, that's point PC here, and where it was, point PL. And it's going to make a vector from PL to PC and from PC to PN. It then finds the angle between those two vectors, indicated here with theta, and then it will tell the robot that it needs to turn that much in order to be pointed in the right direction. These dotted lines right here indicate the bubble around a piece of N that the robot needs to get into in order to have sufficiently navigated to that point. The reason for the parallel lines around the line that the robot will be traveling is because if the robot were to pass through the bubble around a piece of N, we would want to make sure that it could keep track of the fact that it had passed by a piece of N. The reason for this is because it only collects GPS points about every second or so. And so if the robot were to drive too quickly, we might drive out of the bubble before it registers that it was in the bubble. And we don't want to make the bubble too big, or else it may be essentially useless to us, because it could be, a few feet off the sidewalk in the grass somewhere and think it's where it wants to be. And then we additionally have the base station for the GPS RTK. I mentioned this before. So the GPS RTK GPS RTK system is not a new thing for our project. It's been used for previous projects here on Grove City, including the ant tracking robot, which used the high precision GPS to track where an ant would be going through the grass. So we had the base station on hand, but it was a loose unit that we had to carry around and place down somewhere. And we wanted to be able to mount it somewhere semi-permanently so that we could use it and also other people using the GPS RTK could use the base station. So our solution to that was we mounted it on the side of Hoyt Hall. We mounted it semi-permanently because there are better places on campus to be mounting it, but we wanted to be able to mount it within a reasonable amount of time and without causing permanent damage to the side of a building somewhere. We originally thought of using Rockwell Tower so we could have all of campus, but due to constraints because of other RF antennae and interference from the LED in the windows on Rockwell Tower, we determined that Hoyt Hall was a better option. We now have a waterproof GPS RTK base station that can be used by anyone with a GPS RTK rover unit for any project on campus. I'm now going to pass it over to Sarah to talk about the user interface and next steps.
Thank you, Thomas. Hi, I'm Sarah, and I was in charge of developing the user interface for the delivery robot. I created the front end of a web interface using Angular, which is a TypeScript framework for building single-page client applications. The user interface communicates with the robot and is able to control the motors using ROS. The website is hosted on the Jetson Nano and can be remotely accessed from anywhere on the school's network through remote desktop. The Angular portion of the application can be remotely accessed at the IP address of the Nano in a browser. However, when accessing the user interface in this manner, the browser cannot connect to the ROS server, so it currently cannot control the robot using this method. There's a bash script on the Nano that can start up the user interface as well as all the ROS nodes. For the UI, the script will automatically start up the Angular application and open the web page in the browser. The script currently uses a command to start up the user interface using the Nano's static IP address for Hoyt Hall of Engineering. It can easily be modified to start up at the IP address for the student union by switching it to a different predefined command. After a short welcome message, the user interface has a row of buttons with different functions for the user to choose from. This row of buttons is easily customizable and can be modified in the future as the needs of the interface change. Currently, clicking on one of the two buttons will publish a value of either true for the Start Navigation button or false for the End Navigation button to the ROS topic Traveling. This ROS topic provides a way to communicate with the motor control and navigation nodes to either start or end the robot's navigation. Messages are displayed on the screen when a button is clicked to confirm the click as well as the completion of the button's function. These messages can be cleared using the Clear button. In future implementations, the ability to display messages will be useful for printing action confirmations, such as the robot arrived at the destination, as well as error messages. And now I will talk about our successes with the project so far. So far, the robot is a self-contained unit with its own power system. All power comes from the onboard batteries. The robot can therefore move freely without having to be connected to any wires. The robot also has a ROS framework that allows its different subsystems to communicate with each other. Additionally, we have a prototype for object detection and collision avoidance using the LiDAR, as well as a prototype navigation framework using the GPS RTK system. We also have the web user interface that I mentioned, with the ability to start and end the autonomous navigation system. Finally, the robot's motors can be manually controlled using a Bluetooth connection to drive the robot around, as JD mentioned. And now I will discuss the next steps for the project. On the left of this slide, you can see the functional block diagram that we created near the beginning of our project. This represents our end goal for the robot. As the first team to work on this project, we made considerable progress towards our goal and built a solid foundation for future teams to build off of. We have made progress on some of these blocks, such as processing the request, determining the route, navigating, and arriving at the destination, while other blocks have yet to be worked on. Here we have a list of next steps to help guide future senior design teams in working on this project. First, due to budget constraints, we were not able to build a package carriage for the robot this year. However, we were able to have some mechanical engineering students design the package carriage for us as an independent study. You can see their carriage design near the top of the slide. As you can see, the carriage is shaped like a box in order to accommodate the up to 2-foot cubed packages that the robot is required to be able to transport. The tubes that you see in the back of the design are not part of the carriage themselves, but instead show where long tube-shaped packages will go when being carried by the robot. Another future improvement for the robot would be giving it the ability to enter and navigate inside buildings. In addition, the navigation framework will need to be modified to allow for proper navigation between Hoyt Hall and the Student Union. For the sake of simplicity, the robot is currently only able to turn in place, so another step would be giving it the ability to move and turn simultaneously. Finally, implementing a computer vision system or a comparable alternative would take the LiDAR use to the next level. We are happy with the progress that we were able to make on the autonomous delivery robot this year, and we believe that next year's group will have a good foundation and clear steps towards achieving the end goal of this project. And that is the end of our presentation. We will now have some time for questions. Thank you.
Great, thanks team. So we have maybe 10 or 15 minutes. If anyone has questions for the team, again, feel free to use the chat panel or just unmute and ask your question. All right, well, I'll start us off. This is a really a pretty complex project to start from nothing, as you all know. There's a lot of moving pieces here. So I thought I'd ask you maybe just to reflect on the process of integrating so many different pieces. Just what are your lessons learned from that in terms of things that worked well? Was Ross helpful or not to that process? Anything that comes to mind?
I could answer that one. I think we would all agree that one of the biggest things we learned from this project is to break the big problems down into the much smaller, more manageable steps. It's to say, let's build a robot that can drive, a few hundred meters without going in the grass on a predefined path. It can sound kind of complex, especially given the size, but going one component at a time definitely helps to make the project more manageable, seem more achievable. It's a lot easier to say, okay, well, let's go 2 feet, or a much smaller point A to point B, and then maybe let's go a few hundred feet, and then without turning, in a straight line. Smaller steps like that can really break our project up into much more reasonable steps. As far as Ross is concerned, in some respects it was helpful because it helped us to conceptualize our project, each of the smaller subcomponents, and it gave us some existing framework to build off of. In other ways, it proved to be somewhat of a hindrance, primarily due to the lack of documentation. We had to create a lot of our own software from scratch, and the existing ROS framework had many specifications that were at times difficult to navigate or figure out because they had not been very well documented, or just they were not common enough problems for there to be existing solutions out there. So there were some benefits for sure, but there are also definitely some drawbacks.
Hello. This is a very interesting project. You all did a great job. I'm wondering what features ROS or your other software may have to allow you to simulate the motion of this robot from one point from the student union to Hoyt Hall, and do your plan your navigation that way.
I can answer that one as well. As far as simulation, we haven't done much in the realm of literally simulating a 3D model moving. However, we have tested a lot of the individual components separately, and as well as combined some, of course. But some example of some of the simulation and testing, I'll use the proximity checking node as an example. We used the LiDAR. We put it in a fixed position where we knew there were no objects within a set distance of it, and knew that it should not be publishing any warning messages to our navigation node, our motor control node. And we tested this by moving objects into distance within a reasonable distance to be alarmed, and we were able to observe the change in the software that way. Similarly, for the purpose of navigation, Thomas was able to go and collect set data points for the GPS RTK system. And our main drawback for testing that is actually the Wi-Fi connection, since we currently require a Wi-Fi connection to our Jetson Nano to monitor its node outputs and to make any changes that we need to correct the navigation. But it has to be outdoors, where of course the Wi-Fi connection is going to be much weaker inherently due to the routers being inside the buildings. We did discuss very briefly with Dr. Brooks. There are a few options that we may have had, such as MATLAB, or rather, I'm blanking on the name, but some simulation software specifically for power systems, and just trying to navigate, to simulate that the angles were moving and such as that, and things like that.
Thank you.
Great. Other questions for the team?
Yeah, could I ask a quick one? So how much like complexity did you guys need in your software? And I'm thinking more of like on the lines of machine learning algorithms and things like that, to begin to learn what are real objects, what is, something blowing in front of the sensor, things like that. How is that working now, or how do you see it working in the future for like a next team?
I'll go first on that, since I looked a lot into an off-the-shelf open source object detection algorithm that was actually readily available and in ROS, our robot operating system. We did some testing with it. We visualized what it decided were objects. We also tested its frame rate, and its frame rate was high enough to be reasonable for us to respond to within a reasonable amount of time. Our biggest drawback was the accuracy and the lack of I guess practicality rather. Excuse me. Since we were primarily using the LiDAR for proximity checking, we don't need all these advanced algorithms to determine how close something is to our robot. And since the object detection algorithm itself was using quite substantially more computing power than others, we deemed it unnecessary. That being said, in the future, if we wanted to do indoor navigation, I think object detection or even computer vision, which is something very similar, virtually the same thing, would be quite necessary to navigate around and actually navigate, not just avoid collisions, not just stop and start. And that would be doable given our computing platform. But in terms of which algorithm to use, we haven't looked into AI learning. We've only really explored just a couple object detection algorithms.
Thank you.
I hope I answered your question.
Yeah, no, that helped. Thank you.
If a person walks across the robot's path, say within 1.5 meters, how does the robot handle that?
Our proximity, the way our proximity check works currently is if any object is within 1.5 meters on the front or even in the back, assuming it's direction of movement, it will stop in its place. It has a very quick start and stop time, and given the fact that we are not moving very fast, as JD pointed out, we'll be moving at roughly walking speed. We expect to have plenty of time to stop to avoid any possible collision. In the future, we could look into maybe slowing down, but for the purpose of both safety and simplicity, right now our robot, it will pause until the object, in this case a person, is far enough away from the robot, from the LiDAR, at which point it will resume its navigation function.
All right, any other questions? We have time for one additional.
I just want to say great job, guys. Good work there. It's very interesting presentation to hear.
Thank you.
Thank you.
Thank you.
All right. Well, thanks, team. We appreciate your work here.